Everyone, a very good morning. Myself, D. Qasim Wali, Associate Professor, Department of Information Science Engineering, Vidyavardhaka College of Engineering, Mysuru. Welcome you all to this second day FDP on machine learning. Yesterday we had introduction to machine learning session. Today we'll be having session on regression. I hope all of you have watched that video, yesterday's recorded video. Today we'll be having session on regression. And one more request to all the participants, please note down your questions if at all you have any questions throughout these FDP. So all those questions will be answered on the 5th day of this FDP. Please do cooperate because of the bad weather conditions and the location of resource person, we were not able to contact him. So he has recorded and sent the video. Yesterday you have seen that. Hope you'll be having a very good session today and tomorrow and till the last day. I request all the participants to give the feedback at the end only, last day, and certificates will be issued based on your feedback. Okay, no need to give feedback every day, as we have a same resource person. We will have a feedback session at the end, and we'll have a question and answer session on the 5th day itself. Please do note all your questions and raise them on the last day. Happy learning. Thank you.
Hello everyone, welcome to the second session of this series. Today we'll be talking about regression algorithms. In yesterday's introduction session, you would have got a little bit of an idea about your regression algorithm, how exactly it works or what exactly it does. But in today's session, we'll be deep diving into this algorithm, trying to understand how exactly the model is built, what happens in the mathematics side of it, and what different algorithms actually play a role in coming up with this regression line. Okay. Having said that, before we actually jump into regression algorithm, it's actually very important for us to understand different types of data or different types of data points, I would say. So whenever we talk about data points, we can actually classify or categorize them into two different types. Okay, the first one is continuous values, the other one is discrete values. Okay, so what exactly is continuous and what is exactly discrete, right? So continuous values is or continuous data type or continuous data points are those data points which can actually take infinite number of possible values. Okay, for example, speed of a car, right? It can be 20 kilometers per hour, it can be 25 kilometers per hour, it can be 30 kilometers per hour, or it can actually take any possible value, like infinite number of possible values between 20 and 30, right? If you say take the value 20.05, it's a possible distance, right? Or let's say possible speed of the car, right? Or if you take 20.0005, it's still valid and it can be the speed of the vehicle, right? So if you actually think about it, between 20 and 30 you can come up with infinite number of possible values, and everything makes sense for this kind of data. Okay, so coming to the other type of data points, which is discrete, you can't have infinite number of possible values, you can only have predefined number of possible values. Okay. For example, gender of a person, it can be male, female, transgender, maybe these three, right? Nothing apart from these three, right? Or if you talk about country of the person, maybe like 205 odd countries, right? You can't come up with infinite number of values for the country column, right? So this is how you can actually distinguish between continuous values and discrete values. Okay. One more test that you can conduct to see if it is continuous or discrete is mathematical step. So in case of continuous values, you can actually apply mathematical operations. For example, speed of two cars. Okay, the first car is going at 10 kilometer per hour. The second car is going at 20 kilometers per hour. You can actually say that second car is going at twice the rate of first car. twice the speed of first car, right? So because 20 divided by 10, you can do these kind of mathematical operations, and you can say that okay, it is twice the speed of the first car, right? Whereas in case of discrete values, you can't do that mathematical operations. For example, let's say the first person has passed the test, or let's say the first person is from India and the second person is from, let's say, Sri Lanka. You can't just do India plus Sri Lanka by 2, right? It does not make sense. Whereas in case of speed, you can actually do these kind of operations, right? Let's say first car is 10 kilometer per hour, second car is 20 kilometer per hour. You can say that average speed of the car is around 15 kilometers per hour, right? So that is another test that you can conduct to see if the data type is continuous or discrete. But why are we talking about continuous values and discrete values? That is because in machine learning, whenever we work with our data set, it's very important to find out what kind of data set that we are looking at, or what is the data type of each of the column that we are working with. Okay, especially the target values that we are working with. Okay, for example, in case of temperature prediction, you are trying to predict temperature value, right? So what exactly is temperature? Is it continuous or discrete? It is continuous, right? So that is really, really important, because that will actually decide what kind of algorithms you'll be using for building a predictive model. Okay. So just to cut it into short, or just to make it very simple, so whenever you have a target column that is continuous, you have to go for regression algorithms, and whenever you have a target column that is discrete, you have to go for classification algorithms. Okay. And whenever you have a problem where you don't have a target column, then you have to go for some kind of unsupervised learning models, okay, like clustering or something else. Okay. So this is very important, and that is why continuous values versus discrete values is really, really important. So in yesterday's session, actually we saw this chart, right? So let's say I have collected, let's say, information about some 10 houses, or maybe 1, 2, 3, 4, 5, 6, 7, 8, 9 houses. What I have done is I've collected the area of the house versus price of the house. Okay, and what I've done is I've just plotted it on XY plane. Okay, so your x-axis value is your area of the house, and y-axis value is price of the house. Okay, so if you actually take this house into consideration, this is a house which is around 500 square feet, and it's priced at around $300,000. Okay, if you take this house here, this is around 1,600 square feet, and the price is around $550,000. Okay, and if you take this house here, it's around 2,000 square feet, and the price at around 850,000 square feet, right? So what if we want to predict the price of a house which is not there in this data set? Okay, let's say there is a new house that is around 1,300 square feet area, right? What would be the price of this house? Can we use this data and try to find out an answer for this question? Yes, we can. Let me ask one more question before we proceed further. What might be the price of a house with, let's say, 2,200 square feet area, right? So both these questions can be answered by a simple technique called as regression. So in regression, what we do is, given the value of x and y, in this case features and target, we try to come up with a line or a trend that actually decides or defines, or we come up with a line that best fits all these points in the data set. Okay, so if you actually see here, as the area increases, the price of the house also increases, and so there will be an increasing trend, and that is what we try to capture with the help of regression algorithm. Okay, so okay, I won't go into the details of like how exactly I came up with this line, but let's assume that this line is the best representative of all these points. Okay, so how do we use this line to make predictions? Okay, the first question was, what might be the price of a house with 1,300 square feet area, right? So 1,300 is here, right? So what you can do is, once you come up with this line, you actually extrapolate your 1,300 on the line, okay, like this, and wherever it hits your line, let's assume that this is our regression line. Okay, wherever this hits the regression line, try to get the y axis value for that point, and that would be your prediction for this particular house. Okay, so 1300 square feet house will have an area of $500,000. Okay, what would be the price of a house which is 2200 square feet? Same thing, like you will be doing the exact same thing. Instead of extrapolating from 1300, you'll be extrapolating from 2200 and then take the y-axis value as your prediction. Okay, so in this case, if you see, given all these points, we try to come up with a line that best represents all the points. Okay, or in other words, given the value of x and y, or features and target, we come up with a line that best represents all those points, and try to pass through as many points as possible. Okay, um, that is an example that I gave where we were using straight line, but straight line might not be useful in all the cases. For example, in this case, if you see, if you use a straight line here, these points will be missed out. If you use a straight line like this, these points will be missed out. So with a straight line, you can't actually come up with a trend of this. So what you can do is you can actually come up with a curvy line, okay, or curve. Okay, that is also possible, and both of these are actually regression problems. And the first one is actually called as linear regression, and this is called as non-linear regression or polynomial regression. So to make predictions from this line or the curve, what you do is you do the exact same thing that you did in the earlier example. You whatever value of x that you want your predictions for. For example, here the question is what would be the average temperature in Bangalore in 2020, right? So 2020 is here. You take the 2020 value, extrapolate it on the curve that we come up with, and then you extrapolate it on the y-axis, and that is your prediction for the temperature in 2020. Okay, so this is how you make predictions from any regression model. In this case it's all line, but you might have an example where, okay, in this case we are using only one feature and the target. You might have two features or three features or four features. In such a case, what happens when you have two features instead of one feature, this entire problem will get converted to a three-dimensional space. So this will be on one axis, the another feature that we are talking about will be on another axis, and this will be on your third axis. Okay, and instead of this line, we will be coming up with a plane. And in case if your data set has more number of features, like more than two features, then instead of a plane, we come up with a term called or we come up with a shape called as a hyperplane, that is used to represent all the points. Okay, you will not be able to visualize hyperplane in using any technique, but mathematically you can easily represent them with use of an equation. Okay, um, okay, now the next thing that we have to understand is data relationships. Okay, so in this case what happens is, okay, before we jump into regression, we have to understand two types of relationship between your data sets. Okay, the first one is actually called as deterministic relationship. uh, in simple words, what happens, your x value, okay, basically this will also have a feature and a target. So for each value of feature or each value of x axis, you'll always have the same value for y. Okay, for example, in this case we are plotting Celsius versus Fahrenheit. So 40 degrees Celsius is around 100 degrees Fahrenheit, right? So whenever you pass the value Celsius equal to 40, in these kind of problems you'll always get the same value. Okay, 40 Celsius is always equal to 100 Fahrenheit, and that is why the equation is simply y is equal to beta 0 plus beta 1 x, okay, which is nothing but equation of a straight line, right? So this is same as y is equal to c plus mx, or mx plus c. Okay, uh, okay, so in this case what happens, for each value of x you'll always have one single value of y. Okay, the second type of relationship that we are more interested in is actually called as statistical relationship. So what happens in this is, for each value of x you might have more than one or more than one value for y. Okay, for example, I'll take this example here. So we have house area versus house price. Let's say area of the house in square feet is plotted on the x-axis, and price in 1,000 rupees is plotted on the y-axis. Okay. Now, if you actually take any value for x here, okay, let's say 2,000 square feet, right? So you can, okay, it's unlike deterministic relationship. For a 2,000 square foot house, you can actually have two different price values, right? One house might be selling at, let's say, 10 lakh rupees, sorry, it's 1 crore rupees, and another house which might be selling for 1.2 crore rupees, right? So so in simple words, deterministic relationship, for each value of x you'll always have one single value of y. In statistical relationship, for each value of x you might have more than one value of y also. Okay, so because of this, what happens, there will be something called as noise in your data or uncertainty in your data, and using this regression line, we will be just representing all the points, whereas in case of deterministic relationship, you will be able to come up with a line that passes through all the points. Okay, whereas in case of statistical relationship, we won't be able to come up with the line that passes through all the points. Okay, but instead we try to represent some kind of a trend. Okay, and that is what is statistical relationship, and regression algorithms are more useful in working with statistical relationships. Okay, so let's take a live example and try to come up with this line. I'll tell you how exactly the algorithm works, what mathematical calculations happens in the backend. But before that, what we'll do is we'll take a hypothetical example and we'll try to go through the whole data set step by step to understand how exactly a regression algorithm works. Okay. It's the same thing, like we have area of the house versus price of the house. Okay, area on x-axis and price on y-axis, and this is how all the houses looks like. Okay, let's take this house for example. It's around 1,000 square feet and it's around 5 lakh rupees, right? Or it's 50 lakh rupees. Okay, so as you see, as your square feet increases, there is an increase in price also, and basically we can see a trend, right? So if there is no trend, let's say the points are all around this xy plane, then there is no point in building a regression model, because you won't be able to capture some kind of a trend. Okay, so the first question that you have to ask is, given your features and target, is there a trend associated with your data? Okay, so in this case, if you see, as the area increases, the price also increases, right? But if you're not seeing that kind of a trend, if the points are all around this plane, then you shouldn't build a regression model. But in this case, since there is a trend, we'll go ahead and build a regression model. And let's say this is how the line looks like. Okay, trend looks like. Okay, so if you see all the points, they're all like this line that we came up with is best representation or best representative of all the points. Okay, but how exactly do we call this line as best representative? That is because we actually have something called as an error in this model, and we try to check different lines for these data points, and finally we select that particular line that has the least amount of error. Okay, but what exactly is an error? Okay, so if you actually take any one of the data points here, for example this. Okay, so if you actually see, the house is around 1,600 square feet in area, and the price of the house is around 7,500. Okay, in 1,000 rupees. Okay, around 7,500. Okay, but when we came up with this line, and now when we try to make prediction for a house which is 1,600, we will be making prediction along with this line, right? Along the line, right? So the house price would be somewhere here, maybe around 8,000, right? So if you actually see, the actual price of the house is 7,500, but according to our model, the predicted price will be somewhere around 8,000, and the difference between this and this is actually your error. Okay, so okay, that is for one of the data points, right? But you have like hundreds of different data points in this data set, right? So what happens then, right? So just like how you calculate error for one single point, you will be able to capture or calculate error for all the data points in this data set. And this is how it looks like. Okay, this is another example, but this is how the error for each of the data point looks like. Okay, now whenever you build a model, you can't give hundreds of these errors and say, okay, this is my error of the model, right? You have to combine them into one single error. And you can say, if you combine them into one single error metric, then you will be able to say, okay, I have built a regression model with an error of this, right? You can't say, okay, I built a regression model with, you can't list out those 100 different errors, right? So that is why you have to combine all these errors together. So there are different ways in which we can combine them. One of the simplest ways, like adding all the errors together. Okay, but there is a small problem with that. So if you actually see, we have to define our error metric, right? So let's say our error metric is actual minus predicted. Okay, so if you take this example here, some of the data points are above the line, and for those data points your error will be positive, and some of the data points will be below this line, and for those data points your error will be negative, right? So when you just add them together, the positive errors might get cancelled out with negative errors, and as a result you might end up with a model which is really bad but error equal to 0, because all the errors get cancelled out with all the errors. Okay, so summing all the errors is not a good idea. So that is why what we do is we actually use something called as SSE. SSE stands for sum of squared errors. So in sum of squared errors, what we do is we actually square each of these errors, okay, and then sum them together. Okay, so SSE stands for sum of squared errors. So what we do is, since we are squaring each of these errors, positive and negative will get cancelled out, because when you square anything, it always becomes positive. And that is the first advantage of squaring the errors. And the second advantage is, uh, the points that are far away from the line, the error will be higher, and when you square it, the impact of that error will be even more on the model, right? So what it means is, the points which are very close to the line will have less amount of error, and even if you square them, it will not bloat up by a huge value. But if the points are far away from the line, the error will get squared, and as a result they'll have more impact on the total error of your model. Okay, so as a result, what happens, your model will give you much better error value, and that is why we have something called as SSE, which is sum of squared errors. Okay, sum of squared errors is good, but there is again a small problem with that. The problem is, it does not take into consideration the number of data points in your data set. So what we can do is, we can actually divide your sum of squared errors by the total points. Let's say you have two different models. Okay, the first model has sum of squared errors equal to 1000, and the second model has sum of squared errors equal to 500. Okay, which model is better? 1000 and 500, right? You might think that the 500 model is better, but what if I tell you that, okay, this 1000 error is due to like 20,000 data points, whereas this 500 errors is because of only 10 data points, right? Now it makes completely I mean, it makes a huge difference between the models. And as a result, we have another error metric called as MSE, which stands for mean squared error. So in mean squared error, what we do is, we take SSE value and just divide it by the total number of data points. Okay, so in this case, what happens, 1000 divided by 20,000, so it's around 0.02, sorry, 0.2, whereas here it will be like 500 divided by 10, so the MSE is 50. Okay, now if you compare MSE of these two models, you'll see that, okay, this is 0.2, this is 50, so you can actually say that, okay, this model is worse than this model. Okay, uh, just like MSE, you also have one more error metric called as RMSE, which stands for root mean squared error. So in root mean square error, what happens is, you calculate MSE and you just take square root of the MSE value. Okay, so why do we do that? Because we are squaring each of these error terms just to normalize that, or just to like nullify that squared error term. We actually take square root, and that is why it's called as root mean squared error, okay, or RMSE value. Okay, apart from these three values are really good, but one problem with these three error metrics is they're actually not bounded, which means the minimum value for those three errors is 0, but the maximum can be infinity also. So as a result, it is not intuitive enough to understand the errors, and as a result we have one more error metric called as R square, which is actually derived from your SSE only. But what happens is it converts your error metric into a range between 0 to 1. 0 means really bad model, 1 means really good model. Okay, now what happens whenever you have an R square value, you can actually intuitively understand if your model is good or bad. Okay, for example, R square value towards 1 or is equal to 1 means there is no error in your model. If it is 0, it means the model is really bad. Okay, so if you get a model with R square equal to 0.8, it's good. If you get a model with 0.9, it's better. If you get one with 0.95, it's even better. And that is how you can intuitively understand your model. Okay, so this is how your error metrics are defined for uh, regression models. Okay, now you might have a question as to why exactly are we calculating this error? What is the importance of this error to a regression model, right? Uh, the answer is very simple. So the regression line that best represents all the points is nothing but the line that has the least amount of error. Okay, so okay, let's take an example. For example, in this case, if you see all these points, and let's say this is our xy plane, you can come up with infinite number of possible lines in this plane, right? So how do we select, or how do we say that if a line is really good or bad, right? So what you have to do is you have to calculate error for each of these lines. Okay, uh, when I say error, it can be either SSE, MSE, or RMSE. Once you calculate this error, you try to see that particular line that has the least amount of error. Okay, so for example, in this case, let me just do something. Let's say these are our points, and let's say we have different lines. One is like this, the other one is like this. Let's say another line like this, another line like this, right? So what you have to do is for all these points, okay, let me call this as 1, 2, let's say 3. Okay, and let's call our original line as 4, and let's say this is 5. Okay, how do we say that 4 is the best fit, or that line that best represents all the points? It's simple, right? You calculate SSE or MSE or RMSE for any of these lines like 1, 2, 3, 4, 5, and choose the line that has the least amount of error. Okay, this is very simple. But what if we have something like this, right? So let's say this is our first line, or another line that will look like this, another line is slightly different like this, another line is like this. Okay, now in such a case, what happens, it would be very difficult to find out what is that line that has the least amount of error, right? And again, as humans, we can do this very easily, but the computers don't understand, or humans are extremely smart people. Computers are not. We have to tell the computer how exactly to do that. Okay, so for that we have two different algorithms that run in the back end of a regression model. The first one is actually called as least square method. It's simple, right? Once you have a line, you just calculate error for each of these points, error for the line, and you try to get the line that has the least amount of error. Okay, but how exactly computer does that? It has a method called as gradient descent that runs in the backend, that actually calculates some kind of an error for different lines and selects the best model. Okay, so gradient descent is actually a iterative optimization algorithm. When I say iterative, it works in different iterations, and it is optimization because it finds, or it is the algorithm that uses some kind of an optimization technique to find the optimum value for parameters of the model. Okay, let's take a very simple example. Let's take these points here. Okay, and what we want to do is we have to come up with a line that best represents all the points, right? So now, just like how I showed in the previous slide, we can actually come up with multiple lines like this, right? Which line we have to select, right? For that, we use gradient descent. Okay, how exactly gradient descent works? Okay, basically it starts somewhere randomly, and in different iteration it updates the value of these parameters, and then finally it reaches the bottom of the curve where you get optimum value of the parameter. Okay, just to put it or just to give an example to show this. Okay, let's take the same example. Okay, let me just erase everything. Okay, and we have to come up with this line here. Okay, we'll make it even more simpler. Let's keep it as, okay, this line is nothing but y is equal to, sorry, y is equal to mx plus c, right? Or in other words, it is y is equal to beta 0 plus beta 1 x, right? So in this case, what happens, we are given the value of x and y. So x and y are given. So what we have to do is we have to identify m and c, optimum value of m and c, in such a way that the error term that we get with this is minimum. Okay, so how exactly it works? Okay, let's just for simplicity's sake, we'll just ignore the intercept term. We'll just think that, okay, the line passes through the origin. Okay, so the equation of the line is y is equal to mx plus c. Okay, sorry, mx plus nothing. Okay, so just, okay, so y is equal to mx. Okay, so so in this case, the y and x values are given. So what we have to do is we have to find out the value of m in such a way that this error value is minimum, right? Okay, so how do we do this? It's simple, right? Epsilon or error is equal to y minus mx, correct? So what we have to do is we have to come up with optimum value of m, so that our the error value is minimum, right? Okay, so how does this gradient descent work? It randomly chooses some m value in the beginning. Okay, so let's say in this case the optimum value of m is equal to, let's say, 2. Okay, but the algorithm does not know the solution, right? So what it does is it starts with let's say m is equal to 5. Okay, so if you see this chart here, okay, this parameter is nothing but your m, this cost is nothing but your error, and so whenever your parameter value is 5 or your slope value m value is 5, your error of your model will be somewhere here, right? So then the gradient descent understands that, okay, the value that I chose is not the optimum value. So the optimum value is actually in this direction, which means I have to reduce the value of m in such a way that the error decreases. Okay, so what it does is in the next iteration it just adjusts the value of m by a small value. Okay, so in the next iteration it becomes from 5 to, let's say, 4.5. Okay, so the new value of m will be somewhere here, and again it calculates the error. Okay, now the error is somewhere here. Okay, it has reduced from the previous value, but still it is not the optimum value. Okay, the algorithm further knows that, okay, you have to further go in this direction to get the optimum value. Okay, in the next iteration from 4.5 it becomes, let's say, 3.5. Okay, so when it is 3.5, the solution is again somewhere here. The error is less compared to the previous run, but still it is not the optimum value. Okay, so it again adjusts the value of m from 3.5 to, let's say, 3, and finally when it becomes 2, it knows that, okay, the value of error is minimum, because even if you further reduce m value by a small value from 2 to, let's say, 1.9, or from 2 to 2.1, in both the direction the error only increases. Okay, so finally it understands that, okay, this is the solution that we have to use, because if you increase or decrease m value by a small value from this, it will only increase the error of the model. Okay, so this is how gradient descent works. It starts randomly somewhere, and in each iteration it adjusts the value of parameter in such a way that the error decreases, and finally it stops when the error is minimum. Okay, or further change in the value of parameter will only increase the error. Okay, then it will stop. Okay, this is an example where you start in on this side, right? But it is possible that you can start from this side also. Okay, let's say your initial guess or random initialization m was 0. Okay, so what happens when m is 0, your error is somewhere here. Okay, so now the algorithm knows that okay, it is not in this direction, it is on the other direction. So it understands that okay, I have to increase my parameter w or parameter m. I have to increase parameter value so that the error decreases in this direction. Okay, so in the next iteration from 0 it becomes, let's say, 0 0.5, 0 0.9, 1.5, 2.5, like that. Fine, sorry, 1.5, and finally when it becomes 2, it knows that okay, it has reached the bottom of the curve, and it just stops there. Okay, so this is how exactly gradient descent works. This is one of the optimization algorithm that is extremely popular in machine learning, because a lot of other optimization algorithms are actually based on gradient descent. Okay, but this is how it works. Okay, okay, so this is how the gradient descent curve looks like when you have only one parameter to learn, okay, or optimize. But when you have two parameters, let's say the equation is y is equal to mx plus c plus epsilon. Okay, epsilon is an error. So in such case, what happens? Your entire problem gets converted to a three-dimensional space. Okay, so your beta 0 or your c value is on one axis, your beta 1 or your m is on another axis, and your error is on the third axis. Okay, so how exactly it works? Again, initially the gradient descent will randomly choose some point, okay, some random value for beta and beta 0. So let's say it's here. It knows that okay, this is not the optimum solution, so it knows in which direction I have to adjust beta 0 and beta 1, so that I go down the this bowl. And finally what happens, it takes multiple steps or multiple iterations, and once it reaches the bottom of the bowl or the curve, it understands that okay, this is the optimum value or the least error that I can get, and the corresponding beta 1 and beta 0 values is your optimum value for beta 0, beta 1. Okay, so this is the algorithm that actually does all the job in the backend for a regression model. Okay, uh, okay, again in this case we have only two parameters, right? Because what happens, the equation is y is equal to beta 0, which is your intercept, plus beta 1 x, right? You have one feature and the target, right? So what if you have two features? Okay, let's say x1 and x2. In that case, this entire equation will be totally different. It becomes beta 0 plus beta 1 x1 plus beta 2 x2. In this case, you have three parameters to learn, right? How do we represent that here? You can actually represent them mathematically, but visualization is not possible because it will be a four-dimension space. uh, you can't visualize it, but mathematically you can easily write an equation and solve the optimization problem and get the optimum value for beta 0, beta 1 and beta 2. Okay, so this is how gradient descent works. Okay, uh, if you see this example here, this is an example of gradient descent in real time. Okay, so what we have is we actually have some data points here. Okay, so these are all the points that we have, and this is the initialized line. Okay, if you see this line, uh, it has some random values for beta 0 and beta 1. Okay, in this case I think beta 0 is around 2, and beta 1 could be something like 0.1 or something. Okay, or sorry, 10, or yeah, it is 10, right? Because if you see delta y divided by delta x, right? So if you see, if your whatever, like it's a very high slope, because if you see this is in fractions and this is in 0 to 8. Okay, so anyway, but the optimum solution that we need is a line that best represents all the points, right? So how exactly gradient descent works? Okay, so if you see, this is the initialization with some random values for beta 0, beta 1. In each iteration it will actually adjust beta 0 and beta 1, and finally when it reaches the solution it just stops. Okay, I'll just play this video and you can just see how gradient descent actually works. Okay, let me just do it again. Okay, now if you see, in each iteration it knows that in which direction I have to adjust this beta 0 beta 1 values so that the error decreases, right? So finally when it comes to this line, it knows that okay, this is the optimum line. Whatever changes I make to this line, error will only increase, right? So it will stop here. Okay, uh, one more very important concept here is called as learning rate. Okay, this gradient descent is an optimization algorithm which uses a parameter called as learning rate. Okay, so what exactly is this learning rate? Learning rate is simply the step that it can take, okay, or the adjustment that it can make. Okay, so if your learning rate is too big, then what happens, the in each of the iteration the algorithm will adjust only by a huge value. So as a result, what happens, you might overshoot this problem, right? Let's say this is your line, and in one iteration it says that okay, adjustment is only this much possible, right? So in the next iteration it becomes like this, in the next iteration it will never come, it will never reach this line, it will overshoot this, and probably you'll never get into this final solution. Okay, so if your learning rate is too high, the model might not give you good results. Okay, what happens if your learning rate is too small? If your learning rate is too small, that what we are saying is okay, the adjustment that happens in each step is very tiny. Okay, so what happens if your learning rate is too small? Your initialization is here, and from here to here, the example that I showed had maybe like 10 to 15 iterations. But if your learning rate is too small, to reach this solution you might have to go through some thousands of iterations, because in each iteration it will only adjust by a tiny value. So from this line to this line it will take a lot of different steps. As a result, you might get optimum solution for your data set, but your model will take a lot of time to train. Okay, so your learning rate should be neither too small nor too big. Okay, it has to be somewhere in the center. Okay, uh, yeah, and finally, okay, just to summarize this entire concept, what is regression? Regression is a predictive modeling technique. Okay, it is used for finding out the relationship between dependent versus independent variable. uh, so this dependent and independent variable can be called in different terminologies. Dependent variables can be called as target. In case of classification, it can also be called as class, or it can also be called as outcome. A lot of different terms will be used. Okay, and independent variables can also be called with different terms. Independent variables, predictors, features, parameters, a lot of different names can be used. Okay, so what exactly is regression used for? Regression is used for predicting continuous value targets. So wherever you have a problem that requires continuous value prediction, you have to go for regression. Okay, so even your time series forecasting, like you forecast what would be the next sales, next quarter sales of a company, right? So that is actually called as time series modeling, which is actually a advanced version of your regular regression model. Okay, so all these things uses regression models. There are different types of regression models. Okay, but three most popular ones or most simplest algorithms under regression are called as simple linear regression, multiple linear regression, and polynomial regression. So simple linear regression models are, it has three terms, right? Simple, linear, and regression. The term regression means we are trying to predict a continuous value target. The term linear means the output of the model is a linear. It can be a line, it can be a plane or a hyperplane. And the term simple means you just have one single feature. Okay, so the equation of simple linear regression would be something like y is equal to mx plus c plus an error. Okay, so the next algorithm is multiple linear regression. It's exactly similar to simple linear, but instead of one single feature, we'll be using multiple features. Okay, so multiple linear regression is again a model where you have multiple features. The model is always linear. It can be a plane or a hyperplane, and regression because we are again trying to predict a continuous value target. Okay, then comes another variant of your simple linear regression called as polynomial regression, where we can actually use some higher order terms and make the line not linear. Okay, for example, if you see when your points are like this, you can't use a straight line to capture the trend, so you need some kind of curved curve, or let's say non-linear line to capture this trend. So for that you will be using something called as polynomial regression. Okay, then there are a lot of other variants of your regular regression models called as lasso regression, ridge regression, stepwise regression, elastic regression. A lot of other regression methods are also there. Okay. Okay, so what exactly is simple linear regression? As I said, the dependent variable is continuous. Okay, which means your target value is continuous, your y value is continuous. Your independent variables, okay, in this case it is not variables, it is just a variable, because as I said, in case of simple linear regression, you will have only one feature, right? So your independent variable can be a continuous value or a discrete value. Okay, so because you have one single feature and one target, your dependent to independent relationship is always a straight line. Okay, uh, because you have one feature, you can't come up with a plane or two plane, a hyperplane or something. It's always a straight line. Okay, and what would be the equation of this line? It's again simple. Y is equal to beta 0 plus beta 1 x plus error. Okay, so we also have a concept called as cost function, which is used by our gradient descent algorithm to find out the best possible line, or the optimum values for beta 0 and beta 1. In this case, the cost function that we can use is, we can use any cost function like SSE, MSE, RMSE, anything. So you just need actual minus predicted, which is your error, square, which is your squared error, and 1 by n, which means mean squared error. Okay, but you can also use SSE or RMSE also. Okay, but all these regression models are good, but they have certain issues. One of the biggest issue is they're extremely sensitive to outliers. Let's say this is our line, these are our points, this is our line, and let's say there is a new point which is here. Okay, okay, let me just try it and show. Let's say the new point is here. Okay, this is an outlier because it does not follow the trend. Okay, so but if you actually include this point in your model, this entire line will be dragged in this direction, and probably your final solution will be something like this. Okay, just because of this one data point. Okay, so whenever you are building a regression model, always make sure to remove all the outliers. Otherwise what happens, your model will get biased towards the outliers. Okay, and as I said, your error metric, whenever you're building your model, you have to use some kind of error metric, right? You can use any of the error metrics like SSE, MSE, RMSE, but I personally prefer R squared because it's more intuitive. Just given the value of R square, I will be able to say if my model is good or bad, right? If it is, let's say, 0, the model is bad. Okay, and if it is 1, the model is the best model, or when R square equal to 1, I have a model with error equal to 0. Okay, and anything in between can be understood from this range perspective. Let's say if our model has R square of 0.5, it's exactly at the center, like it's neither bad nor good, so it's okay model. Okay, but as it goes from 0.5 towards 1, the model becomes better and better. Okay, and at the same time, if it drops below 0.5, goes towards 0, the model is becoming worse and worse. Okay, so this is how you can actually use R square as your error metric for your regression model. This is how simple linear regression works. Okay, you just have one feature, and you are trying to predict the target based on one feature. Okay, example could be the example that we saw earlier, predicting house price based on area of the house. Okay, then comes the second type of algorithm called as multiple linear regression. In this case, what happens? Your dependent variable is again continuous, just like in any of the regression model, your dependent variable or your target variable is always continuous. Okay, that is why we use this algorithm called regression. Okay, and your independent variables. Okay, in case of simple linear regression, you have only one single independent variable, but multiple linear regression is an advanced variant of simple linear regression, where instead of one variable, one feature, we will be using multiple features. Okay, so it can be either continuous feature or discrete feature. Okay, whatever is the case, we will be able to fit our model using multiple features. Okay. So since we have multiple features, your output is again, since it is linear regression, the output is linear, which means it's either a plane. In this case, if you see, we have one feature on this axis, one feature on this axis, and the target on this axis. Okay, in this case, let's say points are on this space, right? So to represent all the points, or the relationship between your feature and target can be represented by, you can't represent it using a straight line, so that is why you have to represent it using some kind of a plane. Okay, if your data set has more than two features, then you have to represent it using something called as a hyperplane. Okay, so because of more than one feature, your equation will be slightly different. Sorry. So because of that, your equation will be slightly different. So your equation will be y is equal to beta 0 plus beta 1 x1, beta 2 x2, all the way up to beta n xn plus the error term. Okay. So for if you actually closely observe this equation, what it means is, for each of the features, a separate slope is associated with that. Okay, so what we are trying to do is, the target is trying we are trying to represent the target based on each feature and its slope. Okay, so actually, if you see this equation of if you see this output of a plane, it can be easily represented by this equation. Okay, you have two features, x1 and x2. This is your x1, and let's say this is your x2 and this is your y. What you can do is, you can represent this plane with this equation, beta 0 plus beta 1 x1 plus beta 2 x2. Okay, and if you have more terms, then this entire shape will become a hyperplane. Okay, so the cost function is again extremely similar to the previous one. In this case, it is MSE, but MS is just my priority. If you're comfortable with the SSE, you can also go for that. Okay, um, rest everything remains the exactly same, like simple linear regression. Your error metric will be again, you can use any of these. Okay, sum of squared errors or RMSE or R squared or whatever you want. Okay, but personally I prefer R squared because it will give me intuitive way of understanding our model. Okay. Uh, Okay, so one thing that I forgot to mention earlier is a column. Sometimes what happens, you'll have a discrete column in your data set, right? If you actually see the previous slide, I said the independent variable can be either continuous or discrete, right? So what happens if you have a discrete value, right? The model will actually throw an error, right? Because it does not understand these discrete values, and when it calculates the error and all, it can't do mathematical operations on these, right? So for that, what we have to do is, whenever you have a discrete column in your data set, you have to do something called as dummy variable creation, or other term for this is one hot encoding. Okay, so what you have to do is, instead of this, you have to convert this entire column into a numerical value. Okay, so how exactly do we do that? What we do is, instead of this, we actually convert this column. Okay, in this case, we have two unique values. We have A and we have B's, right? So what we do is, we convert this into two different columns. Okay, one column is called as A, the other one is called as B. Okay, wherever this value is b, the b column will get a value 1. Wherever this value is a, the a column will get value 1. Okay, so now what happens, instead of using this column, if you use this column, model will throw an error because it does not understand how to work with these string values. Okay, so that is why you have to do this one hot encoding or dummy variable creation. Okay, if you are implementing this in Python, there are a lot of very easy API calls or function calls that you can use for creating these dummy variables of your discrete columns. Okay, so this dummy variable creation needs discrete value as your input in any of your columns. Okay, so this is how exactly your multiple linear regression works. Okay, it's exactly similar to your simple linear regression. Only thing that you have to remember is the equation of your output will change. Or regression, in simple linear regression, it is y is equal to mx plus c. In case of multiple linear regression, it will be y is equal to m1 x1 plus m2 x2 all the way up to mn xn plus c. Okay. Then comes another variant of your linear regression called as polynomial regression. Okay, so in this case, your dependent variable is again continuous. That is why we use regression. Your independent variable is again, it can be continuous or discrete. Okay, and how exactly do you capture this trend between independent and dependent variable? In previous two examples, it was linear, but in case of polynomial regression, it is non-linear relationship. Okay, so how exactly do we get non-linear relationship? We can do that by adding these higher order terms. Okay, so instead of using simple features like x, if you use x square as your feature, the entire problem will get converted to higher order sorry, if you're using higher order terms for any of the features, then the entire problem will get converted to a non-linear problem, and you can actually capture these non-linear trends. Okay, so because of this, your equation of your model will be different. Okay, so equation would look something like this: y is equal to beta 0 plus beta 1 x1 square plus beta 2 x2 beta 3 x3 power 7. All these things are possible in case of polynomial regression. Okay, so only thing that you have to remember is as you use higher order terms in polynomial regression, you'll be able to get extremely complex curves, or your model will become more and more complicated. And if it becomes extremely complicated, you have a problem of overfitting. So whenever you're trying to use polynomial regression, you just have to avoid overfitting problem. Okay, but otherwise everything else remains the same. Okay, in fact, actually, if you actually look at this, okay, so let's say y is equal to beta 0 plus beta 1 x square. Okay, this is a polynomial regression, right? So if you just call this x square as, let's say, z, okay, then what happens, this entire equation becomes y is equal to beta 0 plus beta 1 z. Okay, and if you take a look at this equation, this is nothing but your simple linear regression, right? So polynomial regression is nothing but simple linear regression. Only thing is, instead of using regular feature terms, we'll be using transformed feature terms. Okay, it can be higher order terms, it can be any other nonlinear transformations also, like log x or sin x, anything, like whatever your creativity allows, you can use that. Okay, finally, this is my last slide. See, there are a lot of times people get confused with simple linear regression. So I have a simple problem here. Like, we have 4 different examples, right? Let's call it as 1, 2, uh, 3, and 4. My question is simple: which of these problems can be used solved using simple linear regression algorithm? Okay, so if you think 3 can't be used, the problem 3 can't be solved using SLR, then you're wrong. You can actually fit a simple linear regression model on this. It might not give you good error, like your error will be high, but still you can fit a simple linear regression problem here, right? But if you actually take a look at 4, here you can't fit a linear regression, simple linear regression model, because see, for the same value of x, you have multiple values of y, right? So okay, the whole idea of regression is this, right? Y is equal to, let's say, beta 0 plus beta 1 x, right? You have to come up with beta 0 and beta 1 in such a way that the error is minimum, right? So in this case, what happens, you can come up with this line. You can actually represent this line using beta 0 beta 1, right? In this case, your line will be this, your beta 0 will be around 6, beta 1 will be 0, right? In this case, let's assume this is the line. Okay, as I said, error will be high, but still you can fit this line. Okay, but in this case, what happens, the line that you will come up with will be perpendicular to your x-axis. As a result, what happens, your beta 0 will be infinity and your beta 1 will also be infinity. Okay, and so this problem, the fourth example, can't be solved using simple linear regression. Okay, so linear regression or polynomial regression, or basically regression, is a very old technique, extremely powerful. Like, it's very old and very popular and extremely useful in a lot of use cases. Okay, uh, yeah. So without going into too much detail and implementation, uh, this is what linear regression or regression models are. Okay, so the answer here. Okay. Yeah, so that is the end of regression. Thank you very much. I'll see you tomorrow for the classification session. Okay, so we'll talk about what exactly is a classification model, how exactly it is different from regression models, and what exactly do we do in classification that is different from regression model. Okay, thank you very much. See you tomorrow.